Okay. Yes. Okay. So what I'm going to talk about. Okay. First of all, two things. Thanks for having me. And secondly, at any point of time, if any of you have any questions, comments, please do not hesitate to interrupt. Okay. So what I'm going to talk about is maximizers. Can you guys see this in the back? Johnson, can you see it? Bigger. Okay. You can see it. Okay, so I'm going to do is I'm going to only use this one and that one. I think that might be better. Okay, let me remind myself. Okay, yes. Maximizers for Fourier restriction. To parabola y equals x square and the cubic monomial y equals x cube. These two curves in R2. These talks are based on joint works with Bhopal. Based on 3 preprints. Preprint 1 published, preprint 2 on archive, maybe wrong. Okay, and preprint 3 manuscript more likely. Okay, so today plus epsilon. I do not know what epsilon is. It might be a few weeks, maybe a few months. Okay, but these two are, so I'm going to talk mostly about these two ones and sort of very special cases of the results from these two. Yeah, so this is published. This is on archive. All of these are with Betsy. Okay, so what I'm going to talk about is basically a very simplest possible cases and on in dimension 2. Okay, so let me start. Let me repeat a few things that the 2 previous speakers said. So I'm going to talk about, let's look at the Schrodinger equation. In one spatial dimension. So I'm going to look at I delta t equals del x square, and u at time 0 is given by f, a function of one variable f of x. Okay, so as we have seen, the solution is given by this operator, the solution u, at least for nice f, at least for compactly supported smooth data, let's say, for example, compactly supported and smooth initial data AF, the solution U at time E is given by this integral e power 2 pi I. Take the dot product with this fixed point with the parabola, with the points on the parabola, zeta square, multiply it by the Fourier transform in zeta. Okay. So here, let me write this trivial definition, what they mean by Fourier transform. Fourier transform for a function of one variable is you integrate f against this oscillating factor minus 2 pi I zeta t ft. That's the definition. Okay. So what? Okay, so at least, so this says that at least for nice initial data f, we can solve the Schrodinger operator. So the question is, can you do this for other functions f, which is not necessarily continuous? Let's say, LP functions. And so basically, what this means is that we are trying to. So this is equivalent to, we are interested in a bound of the form u, whether we can do this u of x as a map from x dx, if this is P of R for all nice f. So if we have something like this for all compactly separated smooth f, we have this explicit formula for the solution. If we can prove something like this, so this is in R2, then given any LP function, for example, let's say this is valid for certain P and Qs, then for any fixed LP function, we can approximate f by a compactly separated smooth sequence. And because of this inequality, the corresponding solutions will be a Cauchy sequence in LQ. Therefore, it will converge to a function in LQ, and we can prove that that is the solution corresponding to initial data. Again, let me sort of clarify that the limit that we'll get, it's not actually a function, it's a member of the Lebesgue space. So it's a function defined after a set of Lebesgue. Okay, so this is, okay, so as we have seen, yes? Okay, Jongchen, can you see now? Okay, good. So the question is for which, hello, okay, P and Q does star hold? Okay, so for this, let us introduce a notation that we call the extension of f at xt defined by e power 2 pi I xt dot zeta square f at zeta d zeta. So let me call this G. So that this is extension at f hat. Okay, so what we're interested in this. So by duality, so we are interested in extension of G. This is the Fourier extension operator, LQ of R2, G, where G is this operator of LP of R for certain P and Qs. We are yet to determine what should be P and Q if such inequality holds. Okay. Good. Okay. Now in R2, the claim is that A holds, these are necessary conditions, only if there is a scaling condition between Q and Q, P and Q. So Q equals, let me see, 3 times P prime, and P has to be less than 1 less equal to P less than 4. Okay, so this is, most of it is kind of repetition of what they said, but I want to kind of look at this and where these exponents are coming from, because we are going to use this again and again in our in my talk and also in the next talk. Okay, so how do we get this scaling condition and how do you get this P? Okay, so what we are doing is, okay, so A is, so let me, before that, let me, by duality, this is, A is equivalent to saying that if you have a compactly separated smooth function f, nice, of 2 variables, so f is a function from R2 to nice f, so compact separated smooth, then if we restrict the Fourier transform, which is a nice function, to the parabola zeta square, it's a function of 1 variable. This is LP prime is equal to f LQ prime of R2. For nice if where P prime is this dual exponent given by this condition that 1 over P plus 1 over P prime is 1. Okay. Okay. So how do you get these conditions? The Q equals to P prime, and if this holds, then first of all, there's a scaling relation between Q and P cannot be too large. Okay. How does one get this? So this is called a scaling condition, and this is the rate. Okay. So these are sort of very common. These are called NAP examples. So what we do is take a delta, take a near y equals x square. So let's say this is delta. This is about delta. Take the arc of length delta near 0, and let's test our function to g, where g is the characteristic function of this interval. So take g as the characteristic function. Let me call this C delta. Now this has length delta, so this LP mass is about delta power 1 over P. So I'm going to scale it by delta power minus 1 over P, so that G has LP mass about 1. Right? Okay. So what we are looking for is I want to calculate the extension of the Fourier extension of the piece of the parabola of length delta. Let's say based at 0. So by stationary phase, it says that the extension of G is nothing but this is about delta power minus 2, and this is about delta inverse. The Fourier extension of the piece of length delta is supported on the tube of on the rectangle, because we are in dimension 2, base delta inverse on height delta power minus 2. And well, it's not literally true, but essentially this is what's happening. So 99% of the mass is based here, and it's about constant on this. And the constant is the length of this interval. So it is supported on this, and its height is the length, which is delta times delta power minus 1 P prime. So extension of G is about delta power minus 1 of P times the volume, which is delta. So delta power 1 over P prime times the characteristic function of this rectangle of dimension delta inverse times delta power minus 2. So we can explicitly calculate the LQ norm. And if you calculate the LQ norm, what do we have? We have delta power 1 over P prime times minus 3 over Q. Right? There is nothing special about delta here. You can take delta to 0 and delta to infinity. If you do that, remember, you want this to be at most 1, no matter what delta is, because if you have any hope of having this, this better be true for any delta. Therefore, 1 over P prime must be 3 over Q, which is the scaling line here, equals to P prime. Right? Okay, so that's how we get the scaling line. Yes? I'm sorry. So I scaled F here, so that this has length delta. This piece has length, the LP mass is delta power 1 over P. I scaled it so that this has LP mass 1. Yeah, so extension of G is, what is extension of G? It's constant, right, on this part. So what should be that constant? The constant is the volume of this space, which is delta, times the weight, which is delta power minus 1 over P, which gives us delta power over P prime. Does that make sense? Okay, so that's how. So now take delta to 0 and infinity, which gives us that Q has to be P prime. Okay. Again, I might be too slow, and some of you already know this, but I actually will use this example again and again. So I'm gonna write this one. Okay. So the next thing is that P has to be between 1 and 4. Well, we do sort of same type of example. Instead of taking one delta function, what we'll do is we'll take delta inverse one delta functions. So this has length delta, and around another point take another delta 1, and so on. Take arcs of length delta, disjoint arcs. So if the sum is, if is sum of arcs, let me call the C deltas, Cj's, this is C1, C2, and so on, so that this has LP mass about 1. So how many deltas do I need? Well, this has length, this has mass delta power 1 over P, delta power 1 over P, and delta power 1 over P, right? So we need about delta power sum. So number of such Cj is delta power minus 1 over P. Am I correct? No, this is delta, this is delta, this is delta. So delta inverse many. Excuse me. If I take delta inverse many such disjoint arcs, then delta inverse many such arcs, and this function has LP mass 1, independent of delta. Now, if we look at the Fourier, yes, we will come back to that because we need the Fourier transform to have disjoint support. So we will sort of, we really will not separate it because we'll actually modulate these ones, right? So now, if we look at the Fourier transform of this space, let me call this F delta. Okay, so what's the extension of F delta? We know that each of these pieces looks like a rectangle, right? A base delta inverse, height delta power minus 2, right? So if I look at this, this looks like something like this, delta power minus 2 and delta inverse. We have another one, right? So this will look like something like this. But remember, I want to make sure, so we can easily compute the LP mass of this function. What we want to do is I want to compute the LQ mass of the Fourier transform, Fourier extension. For that, what I need to do is that the Fourier transform of this piece should be disjoint from this piece so that I can easily calculate this, right? So what I'm going to do is I'm going to multiply this piece by a modeling. So if I'm going to, instead of taking this, I'm going to multiply only this piece, v power minus 2 pi I, let's say, delta inverse times E1 dot zeta dot x square. Let's say E1 dot zeta square. Right? So I'm going to modulate this so that the Fourier transform gets translated at a center. If this is center 0, so this gets translated by delta inverse. So what I do is I'm going to get something like this. So they have disjoint support, but again the same dimension. The dimension doesn't change. Another one. So similarly, if I'm going to multiply this piece, characteristic function this times e power minus 2 pi I, maybe delta power inverse times delta power minus 2 times E1 times x, right? So what we're going to do is I'm going to bunch of disjoint rectangles which have same dimension and they also have disjoint support. Again, this is not really true. I mean, this is, in reality, this is never going to happen. These two functions will never have disjoint supports, but essentially they will have disjoint support because outside this they have negligible LP mass, LQ mass. So I can easily calculate so how many of these are there? So if I can calculate the Fourier extension of these F deltas, LQ, yes. E1 is the vector, first vector, any vector would do. As long as I modulate it far enough so that the Fourier transform of this piece gets translated enough, we're good enough, right? We only have delta inverse. So if I'm going to make sure that this piece has centered at someone like 10 times delta inverse, that's good enough, right? And so on. So that's why I said delta power minus 2. Right? Okay. So what's the Fourier LQ mass? Well, how many are there? There are delta inverse many and LQ mass, so delta power minus 1 over Q, and each piece has length delta power minus 3 over Q. Power minus 3 over Q, and this better be less than 1, right? Because each F delta has LP mass 1, at most 1, about 1. If I take delta to 0 now, I get that Q must be less than 4. Right? Okay. So now, this calculation is very important. What I want you to keep in mind is that this example that we have finitely many delta functions supported disjoint from each other. So that and I sort of modulate each copies by different numbers so that not just that they have disjoint supports on the frequency side, their Fourier transform also have disjoint support on the spatial side. That's what's important. We're going to come back to this again and again. This model example. Okay. So now I'm gonna Now I'm gonna come back to discuss the topic, which is Okay, so that's about the so this is necessary condition that if A holds, this must be true, and in fact it is true, and so the theorem is that this is true. I think for the parabola this was given proved in the mid-70s, right? Peppermint-Stein, yes. This will be non-negative. I mean, this is a necessary condition. This is a necessary condition, right? We're trying to find necessary conditions. So I'm not saying that for k equals 4, it will hold. I'm just saying that it has to be less equal to 4. Yeah, it should not be. I mean, see the thing, you have a part of delta, right? So as long as this is positive, we will have this. So you will include the point 0. When you do nap type examples, we can't really delete the endpoint case. We have to do it manually. In the sphere, we can just look at a nap type example. We can say that yeah, the same thing should happen here because there's no difference between sphere and the parabola. Should be, let me see. So maybe, okay, let me make sure that so delta power minus c, each piece has length delta power minus c over q, and we have delta inverse very such. So the LQ mass is delta power minus 1 over q times delta power minus c over q. So something is wrong here. Let me make sure that I did it correctly. Delta power 1 minus 1 over q, yeah. 1 minus 1 over q should be delta power 1 minus 1 over q. Yeah, but yeah, anyway, so anyway, by this example, we can't really rule out x equals 4, but yeah, we can by looking at specific example. Okay. Yeah. Okay, so indeed it is true. This was proved by Peppermint-Stein in the mid-70s, and so the question is, so the natural question is, what happens for other curves, right? So we have seen that A is equivalent to proving Fourier restriction estimates onto the parabola. So the natural question is, suppose we have a curve, right? So this is your S is a curve in R2 or in higher dimension. So for which can we restrict? Can we meaningfully restrict the Fourier transform f at to S. So here S is a curve, one-dimensional manifold in RD, right? So for example, S was TT square, we know that whole. And so when I say meaningfully, it turns out that, so the precise formulation is this. So let the gamma, at least for polynomial curves, it turns out that at least polynomial curves, there is satisfactory answer. So let's say gamma is a polynomial, So each component is polynomial. Then let with lambda gamma is the affine Acklin measure defined by determinant of this d by d matrix. First derivative gives the first column, and the dth derivative of gamma gives the last column. Take the determinant of this matrix, torsion matrix, and taking appropriate power, d times d plus 1. Let's, with this affine Acklin measure, then one can restrict the Fourier transform. Then for any f restricted to this S, let me call this gamma, with respect to the affine Acklin measure, L gamma dt, LQ of L gamma t dt is equal to f LP of RD for each nice f, for all nice f. For which P and Q, the question is for which P and Q does this hold? It should be independent, this implicit constant should be independent of F. The question is, okay, for which P and Q if you restrict the Fourier transform of a compactly separated smooth function to this one-dimensional manifold, can you get an estimate of this form? And so if you look at the parabola, it turns out that this coincides with the parabola because this becomes 1, 0, 0, 1 for the parabola, right? So for when gamma is t square, then the torsion matrix, this matrix is simply 1, 2t, 0, 1. So it's a volume preserving. So the determinant is 1, right? Okay, let me actually, you know what? Okay, t square by 2 rather. So, okay, now, okay, so the two questions. The theorem is, this is a long history. I might not be able to recollect the whole history, so my apologies. But so the major works done by Zolin in 1974 in dimension 2, and there was Drury, mid-80s, Drury, Michael Christ, '80s, Backover, Linsiger, early 2000 or 2010s, and then finally Betsy Stovall in 2016 proved that this estimate holds for the same exponents as for the model case, the moment curve. Let me call this B. V holds for all on the scaling line, so K equals Cp prime and 1 less than P less than 4. So if we instead of we take any one-dimensional, so we are taking in dimension 2, okay, in RD, right? Okay, so this should be, excuse me, D times D plus 1 over 2 times P prime and 1 less than P times D square plus D plus 2 over 2. In dimension D, this holds any dimension. Okay. So at least for polynomial curves, it is a polynomial, yes. At least for polynomial curves, the question of Fourier restriction is almost complete, except for the endpoint bug. Then with lambda gamma denoting the affine measure, if you restrict the Fourier transform for or a compactly separated smooth function in RD to this one-dimensional manifold given by this polynomial curve, if we look at the LQ norm with respect to the affine measure on this one-dimensional manifold, then we have the same estimate as for the model case. So the model case being, in this case, the model case would be the gamma 0 given by the moment curve t square over 2 e power dy d factorial. This has the same regularity as for the moment curve. Yes, the affine measure. Oh yeah, I'm sorry. LQ lambda gamma. Okay. Yes. Okay. So yes. So there are two things I want to say. Number one is that lambda gamma is the optimal measure. Meaning, if you take any other measure mu supported on this one-dimensional manifold, and suppose we have a estimate of this form for any fixed P and Q, then that measure mu has to be absolutely continuous with respect to the one-dimensional epic measure, and its radon-Nikodym derivative is bounded above by the up to multiply constant by the affine measure. And you can see it easily by just playing with the NAB example. If you take the characteristic function of a delta, then if you look at the Fourier transform, then this will give us a lambda gamma of this piece. And it turns out that if I play with this, it becomes the lambda gamma of this C delta, let me call this C delta one piece, should be bounded above by delta as delta goes to 0, which tells that the radon-Nikodym derivative of mu of this piece should be bounded above by 1. And it turns out that this was, yes, if you take any measure on the parabola, then its radon-Nikodym derivative is bounded above by the affine measure. Just by playing with the NAP type example, just one piece, just working with one piece. Okay, so number 2 is, so that's, and then the other one is that the endpoint case is mostly open. endpoint case is mostly open, meaning what happens when P is d square plus d plus 2 over 2. So the question is, does the Fourier extension operator, so let me define it now, f of x e power 2 pi I x dot gamma t f of t dt, the dual of the Fourier extension operator, does this map LP d, let me call this LPD. What? Let me just make it complicated, to LQ, in this case, which is actually Q equals to at the endpoint case. So the question is this, and it turns out that the answer is no. Definitely no. It cannot have strong type estimate. In fact, in dimension 2, this coincides with the restriction conjecture, which says that if we do not have even have restricted weak type at the endpoint. By restricted weak type, I mean, is everyone familiar with the restricted type? We just we will look at, so extension gamma extension of E of F with the inner product supremum over measure of E is 1, measure of F is 1, is infinity. Not 1, this would be in dimension 2, this cannot be restricted weak type. So in dimension 2, for d equals 2, definitely no, it's not even restricted weak type. So if I apply the Fourier extension to the characteristic function of a set, then the supremum is infinity. Yes. So but what happens is in dimension 3 and higher, surprisingly, results are known. Non-trivial results are known at the endpoint. Weak type estimates. So weak type estimates. Weak type estimates are known for simple curves. Meaning, if gamma is of the form, it doesn't have to be a polynomial now, t power a1, t power ad, where a1, ad are just real numbers. It doesn't even have to be positive. I mean, of course, a1 cannot be 0 because it lies on a hypersurface, so there is non-trivial Fourier restriction. But Bach-Oberlin figure proved in 2010 proved that in fact in dimension 3 and higher, in fact, we have weak type estimates. So we have extension of gamma as a map. It maps LPD1 to LQ. PD1 is the what is called mixed storm Lorentz space estimates corresponding to R equals 1, basically. Okay, so that kind of is the history. Yes. Dimension 2 is just for TT square, right? In TT square, we can. Oh, I see. I don't think. If I remember correctly, it was about a sort of tubular neighborhood of. So if you take a finite arc of parabola, take a tubular neighborhood, that sort of functions, sort of test function would be. Okay, so that was proved by Bach-Oberlin figure 2 in the same paper. In dimension 2, we have no hope, but in dimension 3 and higher endpoint, there are endpoint estimates, and the expectation and the conjecture is that that should hold not just for simple curves, for all polynomial curves. That should be true. We should have. Yes. No, I took supremum U1, right? F1. Yeah, but if I take, let's say, 1 over PD, 1 over QD prime, it's the same thing as EZ1 and P1, right? It's the same thing as this. Okay. Okay, so now, how much time do I have? 30? Okay, perfect. Okay, so now I'm gonna come to the, so what my question is, what I'm gonna discuss is, so we know that at least away from the endpoint, we have the same estimates as for the parabola or for the moment curve in the higher dimensions. higher dimension. So the question that I want to address is, are there extremizers for this inequality? So let's look at extension operator, fix a polynomial from R to RD. And so we have this extension operator, Fourier extension operator, equal to pi I x dot gamma t, f of t dt. Okay, so now we have to take lambda gamma t dt here, right? Did I write lambda gamma t? Yes. Yeah. So the dual extension operator given by this. So we know that that extension gamma maps LP of RD to LP of R, LP of lambda gamma to LQ of RD if on the scaling line, so k equals d square plus d. Again, similarly, we can get this by looking at nap type examples, looking at delta inverse many arcs of length delta, and 1 less than p less than d square plus d plus 2 over 2. Okay. So by the way, this is one of the reasons why we can't really get rid of the endpoint bound, because we do know which type bounds holds in the higher dimensions by looking at nap type examples of delta inverse many delta masses. Yeah. But yeah, it is possible to look at very sort of model case. In model cases, it is possible to look at just some Gaussians or constant function on the sphere to get rid of the endpoint case. Okay, so we know that this holds. The question that I want to address is, does there exist extremizers for these inequalities? Most importantly, what sort of sequence would optimize this inequality? For this talk, so although there are results for general family of polynomial curves, in this talk I want to focus on the simplest possible cases and will try to explain the core of the ideas of the proof. So rather than taking any polynomial and any dimension, what I'm going to look at is look at the parabola y equals x square in R2, and as I said at the beginning, y equals x cube. So the theorem is the following. The first one is due to base C. C did it for the paraboloid in all dimensions, and we did it for the moment curve in a dimension, but they coincide. I mean, C did it for TT square anyway. So this is for 216. Is that for each valid P and Q? So that is, remember, K equals 3P prime and 1 less than. So this is the trivial case. P is 1. Less than 4, there exist extremizers. Extremizers corresponding to the parabola, or the extension operator corresponding to the parabola TT square as a map from LP to LQ. So here LP of R, remember for the parabola, the finite terms are identically dt, so LQ of R2. In fact, we can say much more. In fact, every single extremizing sequence comes from a single function, meaning, so what is an extremizing sequence? If we have a normalized sequence, so if Fn has, let's say, LP mass 1 and limit n goes to infinity, extension of Fn, LQ is the operator norm, then this can arise only in the simplest possible cases, only in the trivial cases, meaning along a subsequence and up to symmetry. I'll explain what I mean by this. Fn looks like a fixed function f times little o of 1. Little o of 1. Here, little o of 1 is a function in LP which goes to 0, as it goes, which LP mass goes to 0 and it gets to 3. So you can always remember, if you have an extremizer to begin with, I can always choose an extremizer and sort of perturb it negligibly, right? And then goes to infinity. If I make sure that this perturbation goes to 0, this is the extremizing sequence. And so what this says is that that's the only way we can come up with an extremizing sequence. Okay, so yes. Yeah, so I'm looking at TT square only. For now, for the rest of the talk. Yes, yes, any polynomial curve, yes. Yeah. Yeah, so I should clarify what I mean by this. So we are not going to pretend that the function lives on the curve. We are going to pretend the function lives on the line. And this is the measure, it's a push forward measure of the affine measure. So when I say a function on this is basically will be identified with a function f at t here times lambda gamma t, basically. So it's a push forward measure of the affine measure, and our function will lie on the real line. That's what I mean. Okay, so for the moment curve, for the parabola, yes. Yeah, so we are looking only at R. We don't really identify these two points the same. It might happen. So, yes, it might happen like this. So we're going to identify this point as this and this point as this. We're not looking at functions on the line curve, we're looking at function on the line. That's what I mean, the push forward measure. Yeah, we don't, because we can have something like, as you said, something weird like this, right? Yeah, you can have like this. So how can you identify? Okay. But again, for the model case, it's actually good enough. So for example, TT square or TT cube or any curve which looks like this, let's say TT power 10, there is no problem because it either looks like this or either it looks like this, right? So there's no problem, at least for the monomials. Okay, so for the parabola, there exist extreme measures and every single the set of all extreme measure sequences is compact up to symmetry. And the next theorem is for the cubic monomial for y equals x cube. Again, so theorem part 1, I would say. And part 2 is for gamma equals TT cube by 3 factorial or TT cube rather, doesn't matter. So one of two things must hold. Either there exist extreme measures for the gamma LP lambda gamma now. It's not dt now, it's actually T dt times LQ of R2. And or okay, so either extreme measures exist, or if it doesn't exist, that means all no extreme measure sequence converges. Then there is only one possible way that can optimize this inequality, and it's actually a couple of delta functions. Delta function based at t equals 1 and t equals -1 is the only possible scenario. Or there exists, so given any, let me first write it out, given any extreme measure sequence Fn, so Fn has LP mass 1 and limit n goes to infinity, extension gamma Fn, LQ of R2 going to the operator norm. There exist extreme measures F and G, extreme measures for the parabola, which we do know exist thanks to this theorem. Extreme measures for the extension operator corresponding to the parabola, so that Fn looks like this. Each Fn, okay, I should say, given any Fn, there exists this and a sequence delta n converging to 0. So decreasing to 0, positive sequence such that Fn looks like delta n power -1 over p times, you look at f, you look at this fixed function, you blow it up at t equals 1. So f is fixed, remember, at t -1 over delta n. So this counts for the half of the LP mass of the sequence Fn. And the other one is alpha g minus t plus 1 over delta n bar and characteristic function of t less equal to 2. So there exists given any fn, there exists delta n and two extreme measures for the parabola such that fn looks like this. Of course, yeah, 1 second please. Plus little o of 1, where little o 1 gives to, so here little over 1 of function with LP mass goes to 0 as n goes to infinity. So negligible perturbation, of course, you can have to count for that, where alpha is the supremum of this fixed continuous function. Supremum over s in 0, 1, 1 plus s e power I theta. Look at this, it should be alpha over q, excuse me. Look at the LQ mass of this function as a function of theta. So 0 to 2 pi divided by 1 plus s power p power 1 over p. Okay, so there is this fixed function alpha. It's not that important. So it's some fixed function. This is a continuous function of s. It attains a minimum, maximum. So we expect that the maximum should be either at 0 or at 1 anyway. But anyway, so that each extreme sequence looks like you scale f, you blow up f at t equals 1, and you blow up g at t equals 1, and f and g has this property that extension of tt square applied to f absolute value is almost everywhere extension of tt square applied to g almost everywhere. Not just arbitrary extreme measures of the parabola, they have to satisfy this property that the Fourier extension of these two things corresponding to the parabola are almost everywhere same. There is an identity. Okay. So what are you doing here is the following. So we have this. Now, because there is no self-intersection, we can pretend this function lives on the parabola moment. What happens is the following. It says that either extreme measures exist, there is a function, or you look at t equals 1, look at 1, 1, take up extreme measure of tt square, then blow it up. So this has length delta, this has length delta power minus 1 over p. Did I write 1 over p? Yes. And then another equals minus 1, take another function and blow it up. So this is g and this is f. Couple of delta function at t equals 1, t equals minus 1. If this doesn't optimize the energy, then extreme measures exist. And in this case, okay, and we actually know the operator norm. And in that case, we actually know the operator norm. Tt cube as a map from lambda gamma to LQ is actually just this alpha times the norm of the Fourier extension operator corresponding to Tt square. That's map from LP to LQ. For every P and Q, we can either explicitly calculate the operator norm corresponding to the cubic monomial, and we know exactly what function maximizes inequality or extremizes exist. And okay, so that's the theorem. So what I like to do, how much time do you have? 15. Okay. So what I'd like to do for the rest of the talk today, I'd like to give a very brief sketch of the argument and sort of in particular explain why is the difference between the parabola, such a difference between the parabola and the cubic monomial. And for the next talk, I'll try to give a sort of details about those steps. This one. So if either extremizers exist or given an extremizer sequence, I can find extremizers for the parabola so that I can blow them up at t equals 1 minus 1. And in that case, we can explicitly calculate the operator norm. In the operator norm for the cubic monomial is exactly alpha times the operator norm corresponding to the parabola, where alpha is the maximum supremum of this continuous function. We can, so since I say that we can calculate the energy basically. We can, right? Yeah, we can't say that because it's an existential result. So we have no idea what an extremizers look like. But no, we do not know. Yes. But after listening to your talk, maybe there is a way we can rule out this. Okay, so I should clarify that we don't know actually which one is true. Either extremizers exist or we can identify the extremizer sequences And as you said, TTT power 4, for example, in your case, you said that there is a way we can actually control the radius or the diameter of the cap, right? So we haven't been able to do that, but it might happen that one can do that. So we can just rule this out and prove extreme matches. But at least for now, this is the theorem. Okay, yeah. So the reason, one of the other reason why I want to talk about these simple cases is that although a similar result holds for any monomial curves in any dimension, which is the result of our second paper, essentially this has all of the essential difficulties PTQ. So this is good enough. If you understand this one, then we should be able to. There is no real practical difference between TT cube or any other monomial curves in any dimension. This has all the essential difficulties. So how does someone prove this? This consists of 4 steps. Step 1. So for now, I'm going to write down the steps. I'm not going to explain this today, but I will also why these steps would imply the result. And then in the next talk, I'm going to explain these steps. Step 1 is given any f, given any, again, gamma is either TT square or TT cube. We're only looking at 2-dimensional case and these simple cases. Given any f in LP lambda gamma, reduce f to only finitely many pieces. Finitely many dyadic pieces. Each of which is adapted to intervals of each of which is adapted to an interval. Meaning, given any f, I can write the sum of finitely many pieces. So I can write f as, let me call this f1, f2 plus fk, let's say k large enough, and so that the remainder something, so let me call this a remainder rk has this property. So it has this property. One, each f1, each fk is nice. So each fk is supported on an interval. Each fk looks like this. It's f time characteristic function. There's an interval tau k times where f is about at most 2 per k times the affine measure of tau k per minus 1 over p. What this means is that this essentially looks like those nap type examples. Each fk is supported on an interval of tau k, of length tau k, such that the f is at most lambda of tau k per minus 1 over p. So if I can control the length of this interval, I can simultaneously control the height of the function, right? This is very similar to this nap type example that we have. Essentially, you should think of each fk is sort of nap type example. And the extension of rk, LQ of R2 goes to 0 as k goes to infinity for every f. So for every f, what it means, this is uniform. So for every f, it's enough to look at the first 10 pieces, and the remainder has LQ mass. The Fourier transform of the remainder has LQ mass at most 1 over 10. For each f, we can look at the first million pieces, then the remainder will have 1 over million LQ mass of the Fourier transform. So this is uniform. This number k, this RK will not depend on it. Okay, so that's step 1. This is because of this improved Stybie estimates. Basically, okay. I'm sorry? Tau k is an interval. Tau k is an interval. In R. So remember, in sort of nap type examples, we had this. What we had is the following. We took an interval of length delta and took the height to be delta per minus 1 over p, right? So this is one of these pieces, basically. Essentially, what it says is that if given any function f, I can essentially take it as sum of finally many NAP type examples. That's what it says. Yes, they have decent supports. Yes, yes. Are you out of time? Okay, we can stop here. I can continue the next time. That's okay. People are hungry. Okay. Okay. So yeah. So step 2 is this is my favorite part of the argument is that. So let me call this F1. F1 is the first piece. It turns out that F1 has LP minus 1. So F1 has LP. Remember, if each F is normalized, then F1 LP is at least, let's say, 1 over a billion. I can sort of capture a positive portion of the LP mass, F1. So F1 dictates the rest of F. Meaning, if I know what F1 looks like, then F2, F3, Fk, and everything will depend on F1. Okay, so this was the idea was that what F1 looks like. What I mean by this, if F1 looks like the characteristic function of an interval, so all the other Fk's. But if F1 blows up, so does the other Fk's, which is what we should expect. Because remember, at the end of the day, what we are expecting is that we have two delta functions, right? So if this is F1, F2 better blow up, right? Okay. And this idea that one of these pieces will dictate the rest of the function was introduced by Michael Christ. That we are dealing with extremizers in 2012, I think, when he was working with the paraboloid, averaging over the paraboloid. So T of f of x in f of x plus zeta square d zeta, where zeta is in Rd and x is in Rd plus 1. If you look at the averaging operator with the paraboloid, so for any x, look at the paraboloid, take the integral of f, and he was trying to find whether extremizers exist, and that's why he sort of introduced this concept that we can write f as sum of things, and if I know what the first piece looks like, this will immediately tells us what the other pieces look like. The other pieces cannot behave randomly. I'll explain in more detail what I mean by this. Okay, what details? Okay, so that's step 2. I think actually I'll stop here. It is too much. People are hungry, and yeah, you cannot do math in empty belly. Thank you very much. Any questions? Yes. So the thing is, it's kind of weird. We expect that this should be attended at 0 and 1. So at 0, the value is 1. And at 1, the value is something like 2 power minus 1 over p prime, something like this. But we haven't been able to do so because it's just weird. I've tried like 2 months, but Betsy have tried for like 6 months. But the thing is that this also appeared on the sphere result with Flock. They also had the same thing, but she tried for a few months. He told me that don't waste your time on this. We'll get stuck and we'll produce nothing. Anyway, it's not really important. Just a fixed function, continuous, we can move on with our life. Yeah. Maybe an undergrad can solve it. That's the whole. Thank you very much. Yeah, exercise or summer project for undergrad. I'll let him deal with it. Yeah.